Hello everyone, I am Dr. VRAO. Today I am here with a new concepts, that is solubility product and common ion effect. Solubility product and common ion effect. Before going to learn about solubility product and common ion effect, let me clear one thing, that is solubility. One should consider this solubility for sparingly soluble salts only. I repeat, one should consider this solubility for sparingly soluble salts only, because in sparingly soluble salts the solubility is too small and solution becomes saturated, and the amount of salt that dissolved undergoes complete ionization. I repeat, solubility, one should consider this solubility for sparingly soluble salts only, because in sparingly soluble salt the solubility is too small and solution becomes saturated. And one more thing is that the amount of salt that dissolved undergoes complete ionization, right? Okay. So let us consider the sparingly soluble salt. Let us consider the sparingly soluble salt. Let us consider the saturated solution of sparingly soluble salt, that is AX, sparingly soluble salt is AXBY. Now we are considering the saturated solution of sparingly soluble salt or electrolyte AXBY. When we dissolved in aqueous medium, usually we write it as aqueous. When we dissolved in aqueous medium, because sparingly soluble salt, this salt is in the solid form. When we dissolved this salt in the solid form in aqueous medium, that establishes a equilibrium with AXBY aqueous solution. That establishes equilibrium with aqueous salt solution, right? Because AXBY is a solid. When we dissolved in aqueous medium, that establishes a equilibrium with aqueous salt solution, right? And by the note that I gave in the previous sentence, in the previous statement, in one should consider the solubility for sparingly soluble salts only, because in sparingly soluble salts solubility is too small and solution becomes saturated, and the salt, the amount of salt that dissolved is undergoes complete ionization. So when we dissolve the salt in aqueous medium, that establishes equilibrium with the aqueous salt solution or aqueous electrolytic solution, and which undergoes complete ionization. That also establishes a equilibrium with x moles of A power y minus y, because y is the charge that assigned to A basing on the crisscross method, right, and y moles of B x minus, right. So, solid form is in equilibrium with the aqueous salt solution, and the aqueous salt solution undergoes a complete ionization, and equilibrium establishes between the ions and the aqueous form. So, we can represent, write the whole representation as Ax By solid that dissolved in aqueous medium that establishes a equilibrium, that is x moles of A minus plus y moles of B minus x. These are the charges that we get based on the crisscross method, right. So, there exists a equilibrium between aqueous salt solution and aqueous electrolyte and its ions. So, we can write it is a reversible reaction and there exists a equilibrium, then we can write equilibrium constant K is equal to concentration of A minus power x and concentration of B minus x power y by concentration of Ax By solid, right. Since Ax By is a solid whose concentration remains constant and equilibrium constant is also a constant, and when we multiply these two constants, that is K into concentration of Ax By solid, okay, the concentration of solid or the concentration of solid which is in the concentration of salt which is in the solid, that concentration remains constant. So, constant into another constant. So, product of two constants that gives another constant, okay, that gives another constant A power minus y power x and B power minus x whole power y. Okay. So, this is a constant and its concentration is remains constant, and product of two constants that gives another constant, that is Ksp, that is solubility product, A power minus y power x and B power minus x power y, right. So, solubility product is a product of ions that are formed by the ionization. So, we can define the solubility product as product of ionic concentrations raised with suitable powers of sparingly soluble salt in its saturated solution. I repeat, solubility product is defined as product of ionic concentrations raised with suitable powers of sparingly soluble salt in its saturated solution, right. So, Ksp is a product of ionic concentrations, right, and one more important, most important point, that is the most important that we should keep in our mind, is that there is a difference between solubility product and ionic product, right. There is a difference between solubility product Ksp and ionic product and solubility product. There is a difference between ionic product and solubility product. Okay. So, solubility product is a product of ionic concentrations in a saturated solution, but ionic product is a product of ionic concentrations either in saturated solution or in unsaturated solution, right. So, but one most important point that we should keep in our mind is that when ionic product is greater than solubility product, there is precipitation takes place. Precipitation takes place. Right? And if ionic product is less than solubility product, ionic product is less than solubility product, no precipitation, no precipitation takes place, and solution becomes unsaturated. Solution becomes unsaturated, right. And the third case is ionic product is equal to solubility product. This is the case with very much significance. Ionic product is equal to solubility product, then in this case salt just starts precipitation. In this case salt just starts precipitation. Salt just starts precipitation and the solution is saturated. Solution is saturated and the solution is saturated solution. Okay. You should keep these 3 points in your mind. When ionic product is greater than solubility product, precipitation takes place. When ionic product is less than solubility product, no precipitation and the solution becomes unsaturated, right. And if ionic product is equal to solubility product, in such case, in such situation, salt just starts precipitation and the solution is saturated. Okay. Now, we shall go for mathematical treatment. Now, we shall go for mathematical derivation of a solubility product. Okay. So, AXBY is a salt or electrolyte dissolved in aqueous media and that dissociate as X A power minus Y and Y moles of B power minus X. Let us consider the solubility of this salt is S moles per liter. Let us consider the, already I told you this sparingly soluble salt dissolves, that solubility of sparingly soluble salt is too small. Let us consider the solubility of this salt is S moles per liter. S moles per liter. Its solubility is S moles per liter. Then initially if you take 1 mole of electrolyte at initial state, these concentrations are 0 and at equilibrium 1 minus S is equal to 1 minus S amount decreases from the initial concentration and that amount formed as X moles of S, XS and YS. Okay. And we know that solubility product KSP is equal to concentration of A minus Y power X and concentration of B power minus X all power Y. Okay. And The concentration of a power minus y is xs over x, and concentration of b minus is ys power y. So, we can write it as x power x, s power x, right, y power y and s power y. Then we can write it as x power x and y power y. Here the s power x and s power y. So, s power x plus y. Okay, so KSP is x power x plus into y power y into s power x plus y, right. So, KSP is like the solubility product. Mathematically, we can write the solubility product as x power x, y power y and s power x plus y. Now, we shall write the solubility products of different salts. For example, if you take AgCl is a solid, and when we dissolved in aqueous media, it establishes a equilibrium and that dissociate as Ag plus and Cl minus, and at equilibrium whose concentrations are S and S. Okay, and KSP is concentrations of ionic concentrations raised with suitable powers. Here the powers raised with suitable powers, here the 1 mole, so 1 mole, so we raise it to 1, right. So, and it is whose concentration is S and S. So, S is equal to KSP is equal to S square. So, solubility product is S square. This S is called molar solubility, that S is called molar solubility. So, AgCl is a 1:1 type of electrolyte, that is AB type of electrolyte. It is a AB type of electrolyte. For AB type of electrolyte, solubility product is S square. Now, we shall calculate AB2 type of, we shall calculate the PdCl2. PdCl2, that is a solid, and when we dissolved in aqueous media, that establishes a equilibrium, that is Pd plus 2 plus 2Cl minus, right. So, solubility product KSP and the molar solubility of Pd plus is S and S. I know, I hope you all understand how these S's are come. Okay, so KSP is equal to concentration of Pd plus 2 into concentration of Cl minus power 2. Okay, and this concentration is 2S because 2 moles of Cl minus. So, this is S and this is 2S power square and 4S cube. So, for AB2 type, solubility product is AB2 type electrolyte or salt, KSP is 4S cube. Okay, now we shall calculate the solubility product of AB3, that is if you take AgCl3, it is a solid, and when we dissolved in aqueous media, it establishes a equilibrium, and Ag plus 3 plus 3Cl minus. Okay, so the equilibrium concentrations are S and this is 3S, right. And KSP is solubility product is concentration of Ag plus 3 and concentration of Cl minus power 3 cube. Okay, and whose concentration is S and whose concentration is 3s cube, therefore 27 S power 4. So, solubility product for AB3 type of AB3 type or 1:3 type electrolyte or salt, and another type of salt is AS2S3. It is a A2B3 type or A3B2. Okay. So, when we dissolve it is a solid, and when we dissolve it in aqueous media it establishes a equilibrium. Okay. 2As plus 3 and 3 plus 3s minus 2, 3s minus 2. Okay. And equilibrium concentrations are 2s and this is 3s. I hope you can understand how that equilibrium concentrations came, right. So, Ksp is equal to concentration of As plus 3 whole square and concentration of S minus 2 whole cube, okay, whose concentration is 2s square and 3s cube. This is 4s square and this is 27s cube. Okay, it is 108 S power 5. So, solubility product for A2B3 type of electrolyte or salt is 108 into S power 5. So, these are the calculations for solubility product for various electrolytes, right. So, you should remember one point in your mind: when solubility product, ionic product is greater than solubility product, precipitation takes place, okay, and solubility product is greater than ionic product, no precipitation takes place, and solubility product is equal to ionic product, that salt starts precipitation and the solution is saturated, right. And another concept is common ion effect. Why I am discussing these two concepts together? Because in examinations questions are being asked or problems are being given in the combination of these two concepts. Now, we shall discuss, we shall learn about common ion effect. Okay. Next concept is common ion effect. To understand the common ion effect, let us consider the weak electrolyte of type AB and its dissociation So, weak electrolyte dissociates as A plus B minus, and there is a equilibrium between ionized ions and unionized weak electrolyte. So, we can write the ionic equilibrium constant, that is concentration of A plus concentration of products by concentration of reactants AB. Okay. So, actually K is equal to concentration of products by concentration of reactants. When this is the weak electrolyte solution and it dissociates as A plus and B minus. When if we add another salt or another electrolyte furnishing A plus or B minus ions to this solution, actually this is the weak electrolyte solution AB, and weak electrolyte solution dissociates as A plus and B minus, and we can there exists a equilibrium between ionized ions and unionized electrolyte, okay, and we can write the equilibrium constant, right. when we are adding, when we add another electrolyte furnishing A plus or B minus ions, A plus or B minus ions, that results increase in the concentration of either A plus ions or B minus ions. Okay, I repeat, when we add another electrolyte furnishing A plus ions or B minus ions to this weak electrolyte solution, the concentration of the concentration will be increases, the concentration of either A plus ions or B minus ions concentration increases, right. You can understand easily, when we add A plus ions or B minus ions to the solution, the number of A plus ions or the concentration of A plus ions or B minus ions increases. Okay, it is a general phenomenon. Okay, it is a general thing. But when the concentration of A plus ions or B minus ions increases, okay, so and the concentration of A plus ions or B minus ions, the concentration of products increases. The concentration of products increases. When the concentration of products increases, in this equilibrium, the concentration of products increases, that results equilibrium, that results shift in the equilibrium and shift in the equilibrium to left side, because when we increase the concentration of A plus or B minus ions, K, in order to K to be constant, we should increase the concentration of AB. We should increase the concentration of AB. So when we increase the concentration of, we should increase the concentration of AB. So in order to keep K constant, K is a equilibrium constant, but here the increase in A plus ions or B minus ions, so concentration of products increases, okay, concentration of products increases, but in order to K to be constant, we should increase the concentration of AB. Okay, but this is a long explanation to understand, but there is a easy explanation for this, that is, you know the Le-Chatelier principle. Le-Chatelier principle, what is that Le-Chatelier principle? When the reaction at equilibrium, if it is subjected to change in temperature, pressure or concentration, then equilibrium shifts towards in the direction of stress release, in the direction of stress release, or in the direction to reduce the increased concentration, right. So we are increasing the concentration of A plus ions or B minus ions, okay, that increases the concentration of products. That's why equilibrium shifts to left side. When equilibrium shifts to left side, the degree of ionization of electrolyte decreases. The degree of ionization of electrolyte decreases, because we are shifting the equilibrium to left side. That causes the suppression or that causes the suppress in the ionization of weak electrolyte. So common ion effect is nothing but decrease in the dissociation of weak electrolyte by adding another electrolyte containing common ion is called common ion effect. Okay, so I hope you understand. When we add another electrolyte furnishing A plus or B minus ions, the concentration of A plus or B minus ions increases. The concentration of A plus or B minus ions increases, the equilibrium shifts to left side according to Le-Chatelier's principle. or in order to K to be constant, we have to increase the concentration of AB. Okay. So, when the equilibrium shifts to left side, that results suppress in the degree of dissociation of weak electrolyte. That is, common ion effect is defined as decrease in the degree of dissociation, decrease in the degree of dissociation of weak electrolyte by adding another electrolyte containing common ion is called common ion effect, right. We can, and you all can understand this concept when we are doing the problems. When we are discussing the common ion effect, it is somewhat difficult to understand, but when we are doing problems, we will understand, you all will understand the concept of common ion effect. Okay. And the common ion effect and the solubility product are two interrelated concepts. These two are interrelated concepts because problems are being given in this in the combination of these two concepts. Okay. So, common ion effect is the decrease, the suppress in the degree of dissociation of weak electrolyte by adding another electrolyte containing common ion is called common ion effect. Okay, I hope you all understand these concepts. In the next video, we shall do problems on the solubility product and common ion effect together. Thank you. Thank you for watching.